Hello, everyone. Welcome to today's live broadcast entitled RPLC Method Development Strategies Using Stationary Phase and Mobile Phase Screening and Some Helpful Tools and Tips. I'm Jerry Workman, the Senior Technical Editor of LCGC. I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by MacMod. I would like to share a statement from our sponsor. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography, which means that when they make a recommendation to you about an HPLC or a UHPLC product, it is to partner with you to offer innovative solutions to your complex problems. They use advanced state-of-the-art analytical software to match our product portfolio with your separation needs. The company leverages their 30-plus years of experience in the LC column business and their technical expertise and manufacturing network to help you solve your toughest application problems. MacMod provides up-to-date and accurate technical catalogs and reports from industry-leading separation scientists to keep you informed of new technologies. MacMod is proud to offer halo columns from advanced materials technology throughout the U.S. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark Help widget in the dock at the bottom of your presentation window. I would now like to introduce today's speaker. We are pleased to be joined today by Thomas J. Wege, PhD. Dr. Wege has been with MacMod Analytical since 2008 as their senior scientist, providing pre- and post-sales phone and email technical support to customers, generating applications data, writing technical reports, and presenting scientific papers, seminar and webcasts related to UHPLC and HPLC. At MacMod, Tom has also been responsible for authoring technical writing for marketing and technical literature. Tom obtained his Bachelor of Science degree in chemistry in 1977 from Michigan Technological University and received his PhD in analytical chemistry from the University of Colorado in Boulder in 1982. In 1983, Dr. Wege joined DuPont Agricultural Products at the experimental station, where he developed a wide variety of GC and HPLC trace level, impurity, and assay methods to support product development and improvement, registration, and commercialization of a variety of herbicides, fungicides, and insecticides. With DuPont Ag Products, he championed systematic method development for isocratic and gradient reversed phase HPLC methods using computer simulation software, DryLab, and was a recognized expert in analytical method development, optimization, validation, and management. From 1999 until 2008, Dr. Wege has been an inside application engineer with Agilent Technologies in Wilmington, Delaware, where he provided expert technical support for all of Agilent's LC, GC, and instrument consumables. Thank you for joining us today. Dr. Wege, please get us started.
All right, well, thank you very much, Jerry, and welcome to those in the various time zones. Good afternoon and good morning to you all. Here's a brief overview of what I hope to cover here today in this webinar, and we'll talk about, begin with method development approaches and strategies. Then we'll go through some things that ideally you should know before you begin that work, including, understanding your column, understanding how much pressure it will produce under various conditions, the importance of extra column dispersion and how much your column can tolerate, how to go about measuring it with your instrument, why it's important to measure and know what the gradient delay volume is. We'll mention the ACE method translation and transfer tool. And then we'll talk about columns and condition screening and look at a couple different examples, one with halo columns and one with ACE columns. And then we'll conclude. And I do want to emphasize that in the appendix to this in the PDF, there is some other information on some slides that are not part of the presentation today that might be of benefit to you if you want to take a look at those after the fact. So as with any problem, it's important you're going to develop a method and a separation to understand as much as you can about your sample and the analytes in your sample, if that's possible. Sometimes we're faced with unknown samples and unknown content, and then we kind of have to treat it like a black box. So if you do know what the components are, you can find out what's known in your company, research in the literature, see what other people have done. The complexity of the known or unknown sample will dictate how long the method will be used, will dictate how good of a method you need to develop. Will it be used in one laboratory? Will it be used in your own laboratory and transferred to multiple ones in your own company? Will it need to go outside of your company or around the world? Keep in mind that methods that use detection that are such as the ultraviolet detection, charged aerosol detector, and ELSD all require that the analytes be separated in space. They be completely separated. And LCMS methods require that compounds that have the same molecular weight be separated in space. Here I present in this slide an example of how different levels of sample complexity will dictate what's necessary or what's a way to approach that problem as far as developing a separation. For simple samples, you can possibly work with a single column and a single temperature and a single pH and a single organic modifier, and maybe choose 2 or 3 gradient times and either use an iterative approach by changing the gradient time or the starting and ending points, or to develop a separation, or you may be able to, if you have access to computer simulations such as DryLab or other software, you can use those input runs to then generate a resolution map and be able to find where a good place to work such that you can obtain the separation you desired. Maybe you can even come up with an isocratic separation. But as the samples get more complex, you may need to bring more than one organic modifier, more than one pH into the activity to try to work out a separation of the compounds. And as you see in the bottom half of the slide, in some cases you may need to pick several different phase types and different pHs, different organic modifiers, even sometimes a one-to-one blend of both organic modifiers to really apply all of the different tools and variables that are out there to come up with a solution. And at the bottom of the slide, I wanted to mention that a number of major pharmaceutical companies actually have dedicated groups whose sole job is to carry through the first exploratory method development work and basically come up with something that can be handed off to another principal investigator and their team to then optimize and finalize and validate a particular method. So some folks really put a lot of intent on that, and they come up with a certain subset of columns that they want to use, and that sometimes columns leave that set that they use, and new ones are replacing them. So it can be a big deal when you have really difficult problems to solve. On this slide, I'm showing that a couple different approaches. Approach that you might do if you were working with one single stationary phase and you wanted to apply 1 or 2 or even 3 organic modifiers or a blend of methanol and aceternitrile to a problem. And in the simplest form, you might do a gradient time versus temperature experiment, a 2D experiment, where you choose 2 different times and 2 different temperatures and carry out separations such that you can use those inputs for computer modeling and then find, hopefully, some ideal place to work that not only provides the resolution that you want among all of your analytes, but also has a fairly decent sized, robust space where resolution doesn't change much in that region and gives you some robustness and play to your method. It also is beneficial in some of those cases if you can run intermediate settings, such as in this case here, halfway in between 25 and 50 degrees C, halfway in between 15 and 45, like 30 minutes, and then you'll have those intermediate runs till you can do some peak tracking. On the right-hand side, I'm showing a different approach that also can incorporate that computer simulation, in which you choose a particular column geometry and particle size, and then you choose several different phases with different types of analyte stationary phase interactions, and you screen those different phases with multiple organic modifiers at one or more pHs, and you fix the temperature, ideally at a low value, such that any other higher temperatures that you run later for optimization will all fall below the pressure max of your system. And when you take the results of all those types of screening experiments, you can look at a number of different things for judging which one's the best one to proceed with for further optimization, and that's the number of the peaks that are detected, the number of resolved peaks, the average resolution, which combinations have the best overall peak shape, and so on. And then once you can select one or two of those combinations, then you can take that further and do a 2D temperature and gradient time optimization, or even a 3D optimization for further refinement of that method. So what should you know before starting with this type of a screening approach? Well, it's good to be able to predict, first of all, know what your pressure limits are on the instrumentation that you'll be using. A lot of people consider 400 bar to be the max for HPLC, and various intermediate UHPLCs have a limit of 600 bar, some have 1200 to 1300 bar, but you want to use as your guide somewhere in the 25 to 30, 35% of that maximum pressure as your limit, so that it gives you some leeway for future work that can keep you well away from the pressure max of the column or the system. It's also very beneficial to understand and know what your extra column volume and dispersion is, and that makes up the things I have listed here: your tubing length and ID, injection volume, your flow cell volume if you're using UV or other detection like that, your data acquisition rate, your detector time constant. And I mean, a lot of the UHPL systems that are on the market today are so-called low dispersion instruments, but some are not as low as you think they are, and some manufacturers have actually made kits that you can buy or that you can put together yourself with parts that will allow you to get a more optimized system. And lastly, it's important to know what your gradient delay volume is for your instrument. A real quick look at Van Deemter plots for totally porous and superficially porous particle columns. On the left-hand side, a 5, a 3.5, a 1.8, and a 2.7 fused core or superficially porous column. The upper ones are 5, 3.5, and 1.8 are fully porous particles. And you can see that as the particle size gets smaller, the Van Deemter plots get flatter, and you also see that the optimum is broader for where the best performance is, the lowest plate height or the highest number of plates. And all these things are important to have some sort of a mental image of, so that you're working with a column, with your particular column, so that you're using it at the right flow rate and linear velocity to get the best performance out of it. On the right-hand side, I show Van Deemter plots for different 2, 2.7, and 5 micron halo columns, superficially porous columns. And you note that the halo 5 has an optimum that's a little bit less flat here in the upper trace, and then the 2.7 micron has certainly a lower optimum, meaning it's got more efficiency, and then the 5 micron, and the 2 microns even lower yet. And with those superficially porous particles in the smaller diameters, they have a broader, flatter Van Deemter plot, which is one of the advantages of those types of particles, that you can push them a little faster than their optimum and still maintain most of your performance. So how does one know how much extra column dispersion your particular column can take? Now, we're going to be talking about columns in shorter lengths and narrower IDs. And this plot compares a totally porous 5 micron and 3 micron, the upper two traces or lines, and the bottom two are halo 2.7 and 2 micron particles, respectively. And there's an equation you can use, and you can put in how much of your theoretical resolution or efficiency you want to maintain, and you can see that in the bottom part here, your sigma squared extra column is directly proportional to the column volume and to the amount of retention, the K value in isocratic mode, and inversely proportional to the theoretical plates on the column. So, columns that have smaller volume and have larger plates, that is more efficient, are going to tend to be able to tolerate less of your extra column dispersion. There's different ways to measure extra column dispersion. There's the no column method, where you replace the column with a zero dead volume union and inject a very small amount of a UV absorbing component. And then you can print out the resulting trace and measure the tangents to the sides of the peak and calculate the baseline for sigma width, and then convert the distance from millimeters into minutes and multiply by the flow rate to get your milliliters and square it after you've converted it to microliters and get your microliters squared that way. One of the other ways that's beyond the scope of what we're going to talk about today is to use a homologous series of analytes or a group of analogous analytes like these alkyl phenones or some simple aromatic homologs that have just a single substituent on a benzene ring. And basically you run isocratic separations, say for example at 50% acetonitrile or whatever, and you can actually plot the sigma squared versus the retention time, and under those conditions the equation is such that your y-intercept is your extra column dispersion in microliters squared, and the slope of the curve is 1 over the plate count. This last one is the most modern approach that's been described by Georges Guillochon and Fabrice Greedy of Waters now, and that's discussed in the appendix. And in this case, you use a similar sample as described above, but you use a different equation to, in this case here, the sigma squared extra column is embedded as part of the slope. So anyway, that's beyond what we can talk about today, but there are ways of getting estimates of the dispersion. Here's an example of what I just talked about, where you draw the tangents to the line and so on, and you can look at this after the fact, but I basically discussed this verbally. We did some experiments prior to HPLC 2018 with some 3x50 columns in both 2.7 and 5 micron particle sizes with halo columns, and we were able to measure the amount of dispersion as a function of some reasonable usable flow rates for 3 millimeter columns. And you can see hopefully here that the amounts for the Agilent 1200 were, the dispersion does tend to go up slightly with flow rate over this limited range, and that in the bottom part of this slide on the left, a standard configuration with 0.178 millimeter ID tubing in normal lengths and a 14 microliter flow cell with a very slow data rate of 13.7 hertz that a Agilent 1100 has, that the dispersion is quite a bit higher, ranging from around 50 to 62 microliters squared, compared to the very low numbers obtained on the 1200. Excuse me. What you can see here in the middle of the slide on the left is that you can make some changes to the configuration and bring that dispersion way down, even with the very slow detector rate of nearly 14 hertz. So you can really approach very closely what the performance you have on a more modern instrument with a faster data rate and a small flow cell. And this impacts not only isocratic plate count, but in the bottom right, I'm showing that, even for a gradient separation on a 2.1 by 50, 2.7 micron column, that your peak capacity is actually halved between the optimized 1100 system and the standard 1100 system, going from about 60 peak capacity down to close to 30. Here's a quick slide that shows a ranking of different instrumentation and the amount of extra column dispersion in microliters squared. And I've highlighted the Agilent 1100 quaternary system that I talked about on the previous slide. And here the literature value that was been reported was around 30 microliters squared, and we were able to reduce it down to around 10 to 14 microliters squared. And as I mentioned before, some brands and models do have kits and parts that allow you to make these kind of changes and improvements, such as what I described. It's important to know what your delay volume, your gradient delay volume, sometimes referred to as dwell volume. It's important to help you document your own methods and when you put those in writing so that others can repeat your work. And it also makes it easier for method transfer for yourself and method translation, as well as it makes sure that by having that number and knowing how much equilibration time for your given column size, make sure that you allow enough time for completion of the gradient or for the proper amount of re-equilibration. This is especially important if you're doing computer modeling and generating data that's going to be used as inputs for that. And here's a little slide that shows and describes the procedure for doing that. Again, you use the zero dead volume union. You have acetone as a tracer as your B solvent, and you carry out a no injection run where you monitor the baseline at 254, 265. You get a sigmoidal curve like this, and you use an equation here to get the delay time by taking the time that halfway up the sigmoidal curve goes and subtracting half of the actual program gradient time to get your delay time, and then multiply by the flow rate to get your delay volume. And I do recommend putting a half a minute or a minute hold to give yourself a good flat portion here to make your measurements thereof. Wanted to mention very quickly that we do have an ACE LC translator tool. It's been developed by the manufacturers of ACE. It's available on our website at this link, and it contains a number of different tools for method translation and transfer for isocratic and gradient methods. Has a little procedure, much like on the previous slide, for measuring delay volume or dwell volume, even for measuring extra column volume, column porosity. And what's really nice is when you're doing some of the screening or doing any kind of overnight runs or whatever, it can do a quick and dirty, pretty good estimation of how much mobile phase in both reservoirs you're going to consume. So let's talk about method development. That's what we were here for. So basically, we're going to screen stationary phases and mobile phases, including the modifiers and possibly the pH. For HPLC systems, you can use a short column like a 3x50 or a 3x100 in a 3 micron size. For UHPLC, it's your choice, a sub 2 micron or a 2 micron column, a superficially porous particle column. And by choosing these sizes, you're going to have plate counts in the 10, 12 to 15,000 plates, which is a good amount of resolving power for doing this screening work, and may even end up being the size that you end up with. And typically, you can you may have to go as large as 100 millimeter for more complex samples with 10 to 20 analytes, but in general, a 50 or a 75 even millimeter length can do the job for you. The other thing you want to be able to do is to decide, what your gradient starting and ending points are and what your gradient time is. And the gradient retention equation here with K star and gradient time and flow rate and gradient range, column volume, and the S value is that, you can pick ideally some K star value between 3 and 9 for choosing what your starting and ending points are. If you start too wide, you can always truncate that gradient range by if you initially had started from 5 to 95% organic, and you find that most of your components are more hydrophobic and they're eluting later, then you can maybe start at 50% and do your screening experiments from there. However, you really don't know with an unknown sample, so it's best to start wide and then to reduce later. Or in some cases, you have some that are very polar and then some that are intermediate and some that are a little bit more hydrophobic. So you need the entire range for the screening experiments. And the left example shows a 50 by 2.1, 2.7 micron column with a porosity of about 0.5, and to get a K-star value of 3, you need about a 3.2 minute linear gradient and an overall 6.1 minute run. For HPLC, they're using a 3 by 75 millimeter column as an example with 3 micron particles. It ends up being about an 8-minute gradient for a K-star of 3 from 5 to 95%, and overall runtime, including equilibration, of about 17.5 minutes. And both of these examples that I put on here use 10 column volumes and 2 delay volumes as the amount of equilibration. Just a real quick review of what the factors are that affect selectivity the most, and here I put column stationary phase at the top. Some of these first top 4 are about the same in value, although pH certainly can be the most powerful for ionized analytes. All of these various parameters affect selectivity or relative retention. For gradient separations, all of the ones on the left-hand side are in play that were for isocratic, as well as gradient steepness, and that is your inverse of K-star, and that's affected by, as the gradient equation shows here, these various parameters: time, flow rate, gradient range, volume, and component that's a function of the molecular weight of the analytes. And of course, gradient delay volume also can have a significant effect on selectivity, especially for compounds that are slightly retained or barely retained. It's also important to know that that's why we're using both organic modifier and gradient steepness, or I'm sorry, gradient stationary phase and organic modifier, as well as pHs. But when you apply these various parameters in concert, you can magnify the impact of the changes in selectivity, and it works on the basis of the square root of the sum of squares. So if you have values around 0.2 for organic modifier and gradient time, if you pull those together, orthogonal column and gradient time, you actually bump up the impact of those to almost 0.3 versus the 0.2 or nearly 0.2 that they have individually. So now we move on to an example. We're going to show an example with halo phases, and I'll refer you back to what's been developed, a theory that was developed in the early 2000s by Dr. Lloyd Snyder and Dr. Peter Carr and Dr. John Dolan, which they used an empirical characterization to support this theoretical model that has various parameters of the analyte and of the column that can be determined through some carefully and wisely designed experiments, isocratic experiments that they use to characterize columns. And there's probably 600 or 700 columns that have been characterized by Dolan's lab and now by Dr. Dwight Stoll, his group is now in charge of doing that. And of course, he took his John Dolan's spot in LCGC magazine in the troubleshooting area. So he's responsible for characterizing these columns. And if you were to look on this website here, you can see that you have a halocyatine, phenylhexyl, ES-cyano, and amide, and a PFP. And this F sub S value is really the smaller this number is, the closer these various phases are to each other. But when you're doing method development, you like to have a nice spread of these so you can see different modes of interaction, but also ones that are going to be different from each other in selectivity. And the magnitude of these F sub S numbers gives you an idea of how dissimilar the phases are, or if they're close together, how similar they are. So this first example uses the 4 different phases I show here: C18, phenylhexyl, ES-cyano, and RP-amide, 2 different organic modifiers, 4 different pHs, 2,8 and 3,8 with ammonium formate, and 4,8 and 5,8 with ammonium acetate. And the goal is to try to find 1 or more combinations that could be optimized for a good separation of this mixture. And this is a blindly prepared mixture where part of the compounds were known, and then the latter 7 or 8 were not known to the analyst, which is myself. And so I got my collaborators at AMT, Advanced Materials Technology, put together. I didn't know how many components were present. We started out with working with a 3x50 2.7 micron column, and the conditions you see here: 30 degrees C, 2 to 90% organic, and then a 10-minute gradient time. Again, we're shooting for something in between 3 and 9. And we used an Agilent 1200 binary system. And this is the gradient we ran. And we're going to produce chromatograms like, with each of the phases with acetylnitrile and with methanol, and at each of the different pHs. Well, how do you go about looking at these? Well, you can look at them at least a couple different ways, where you look at the 4 phases at a given pH with a given organic modifier, and by inspection or otherwise look to see which ones give the best overall separation, the most number of peaks, and the best peak shape. And the same is true for methanol and the other pHs, 3,8, 4,8, and 5,8. The other approach is to take and put together the various phases at the different pHs and then compare them that way. So the subsequent slides, and I'm not going to show you all of these because there's a number of combinations here, but on the succeeding slides we have the total number of peaks in a little blue oval like this, and then we have the number of peaks on the nominally left-hand side of the chromatogram, and also on the right-hand side pointing in this direction. So we see here that with the 4 different phases at the same pH, 2.8 nominally, you can see that as far as this is concerned, the phenylhexyl looks the best among these 4 at this pH. That's the first approach that I described. And these are just blown up portions of this chromatogram here and here, where the peaks are closely eluding in this narrow range. The other way of looking at it is taking the C18 phase and the other phases at the different pHs and looking there. That way you can see what happens to the various peaks as the pHs change from 2,8 to 3,8 to 4,8 to 5,8. Again, here there are 2 different combinations that have 19 peaks separated and 2 that have 18. To make a long story short, these ended up being the combinations that looked the best of all of the combinations that were run. 2 of them were at pH 3.8, one with the ES-cyano and one with the phenylhexyl with acetylnitrile. The one with the cyano column was with methanol. And the bottom 2 were phenylhexyl at 2.8 and phenylhexyl at 5.8. The little stars here meant to show that there's these 5 major large peaks here, and when they were all either mostly separated or partially separated, I starred them with the 5 pointed star here. So another way of picking out which is the best one, and really any of these could have been moved forward for optimization. The 3 out of the 4 had 20 peaks observable. Now, from 10 and 30-minute runs and input into DryLab 4 software, we end up with a predicted separation that looks like this. And then when I ran those conditions here, those simulated conditions in actual, it shows the peaks, and the peak shape there turns out to be there was a degradant of one of the components there as well. So again, I don't necessarily recommend you run every organic modifier and blend in every phase you can think of and every pH, but it gives you the idea that, sometimes you can't really say a priori what's going to be the best combination that's going to work, and it's not necessarily true that methanol is always going to be better than acetylnitrile with a phenyl column or with a cyano column, et cetera, as has been sometimes reported. This next example uses the diverse selectivities of the ACE Excel product line, which is a super C18 broad pH range, which has an encapsulated end capping, a phenyl alkyl phase, the C18AR, a pentafluorophenyl alkyl phase, the C18PFP, a long chain cyano-ES, which can even be used in normal fees, even though it has a long alkyl linker, and a polar embedded C18 amide phase, which has a little bit longer linker than most of the columns on the market that are polar embedded. Real quick look at the properties of these, and I'm not going to go through these one by one, but you know, they're all end-capped. The Super C18 is a broad pH range phase. 4 out of the 6 are really 100% aqueous compatible in isocratic mode, so they can be used like that as needed, these last 4 here. The mixture was a 15-component sample that contained bases, acids, and neutrals, and those structures and names are shown here. And again, we're going to apply, in this case, a 2.1 by 50 millimeter totally porous 2-micron column with plate count around in this range. Again, most of the instruments on the market today, including the best of the best, cannot really give full performance of a column of this volume and efficiency in isocratic mode, but they do perform well in gradient mode. In this case, we used a 4 to 80% gradient in 8 minutes, 35C, half a mil a minute, and we used 2.7 and 4.75 phosphate and ammonium acetate, respectively. And for the broad range pH column, we also did a run or two at pH 10.5 using ammonium hydroxide. And for the future, for subsequent slides, the number of peaks that were separated for each combination and column is shown in a yellow oval like this, and we're paying particular attention to peak shapes among them as we make a decision as to which one to go forward with. Again, in each one of these slides to come here, they're all labeled in the same way. The amide phase is always in the top left, and the C18AR top right, et cetera, et cetera. This first comparison is for acetylnitrile at pH 2.75, and you see that actually 4 out of the 6 have 13 peaks that are discernible here on this 8-minute gradient, and from 4 to 80%. And if you were to rank these, I guess I would rank them C18 amide and C18AR being the top 2, followed by the Super C18 as ones that you would take for further optimization and complete separation. And this one is the same pH, 2.75 with phosphate, but using methanol instead. And in this case, the Super C18 column comes out on top in the bottom left trace, followed by the C18 PFP here right above it with 14 components separated. Moving to acetylnitrile, back to acetylnitrile again, but raising the pH to 4.75. The ranking is PFP, C18 amide, and C18AR. And again, 14 components separated here, 13 and 13 for the other 2 second and third place finishers here. Lastly, the slide with methanol and pH 4.75 ammonium formate. In this case, the Super C18 came out number 1 with 14 peaks separated, followed by the C18AR, which I gave a little bit more weight to, even though C18 PFP had 13 as well, because of the potential for being able to optimize this more readily. And this slide, this last slide, this is runs with the Super C18 with ammonium hydroxide at 10.5 pH, and I'm showing an 8-minute gradient and a 24-minute gradient here. 11 components separated under these conditions. when you use those inputs for dry lab, you end up with a 11-minute separation from 4 to 58%. But unfortunately, one of the stronger acids, kumaric acid, comes out in the void under both cases. So we would probably have to rule this out if you really want to do quantitative work, if you were going to try to use this. But the peak shapes at high pH for a lot of these bases, and of course for the neutrals, is quite good at high pH. And here's the summary. So the take home from this is that depending upon the pH and the organic modifier that you use, these 4 phases that I highlighted here in yellow are the ones that tended to come out to be the ones most capable of being further optimized most readily. And the super C18 did produce a high percentage of symmetrical peaks at pH 10.5, but one analyte showed no retention under those conditions and probably would have to be passed by. So in conclusion, I just hope I've come across and given you the impression that it's pretty powerful to use different stationary phases with different modes of retention, whether you're starting from scratch with your method development and doing a holistic approach, or whether you've done a little bit of work with one phase and you want to compare a couple other different phases. You can drop in the same size column or whatever into those methods and conditions if you want to see what the impact on selectivity and resolution is. And a method development strategy that does use different stationary phases, different organic modifiers, and occasionally even an organic modifier blend, and different pHs can be a very powerful approach for identifying conditions that you can then more easily optimize and make robust. And that there are calculations and tools available that make it easier to figure a lot of these things out ahead of time to a degree, that you can't substitute for the screening experiments, but you can do a lot to make all those things be more successful and more productive. So with that, I will hand it back over to our moderator, Jerry, and he will take it from there. Thank you very much for listening and attending.
Well, thank you, Tom. I'd now like to ask our audience to participate in a brief polling question. Please click directly on the screen to enter your answers. Here's the first question. Did you learn something new during this webcast? Yes or no? So I'll repeat the question. Did you learn something new during this webcast? Yes or no? Thank you for participating in our first poll question. Now I'd like to ask our audience to participate in the next polling question. Please click directly on the screen to enter your answers. And here's the question. This is open-ended. What did you learn? Please enter a statement about what you learned. I'll just repeat this. What did you learn? Thank you for participating in this poll. Now I'd like to ask our audience to participate in our final polling question. Please click directly on the screen to enter your answers. Here's the question. From which manufacturer do you currently purchase your columns? Waters, Agilent, Phenomenex, Restec, Merck Millipore Sigma Aldrich, Thermo Fisher Scientific, or MacMod Analytical? I'll repeat the question. From which manufacturer do you currently purchase your columns? Waters, Agilent, Phenomenex, Restec, Merck Millipore Sigma Aldrich, Thermo Fisher Scientific, or MacMod Analytical? Thank you for participating in our polls. Thank you, Dr. Wege, for such an informative presentation. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. We'll begin with our questions. The first question, I can't run 5 or 6 different stationary phases for every method development project. So how can I choose which ones are most likely to work?
Okay. Of course, people really like C18 phases, so you could always consider using one of those. With some of the phases that are out there now, I guess if I had to choose, I would choose like a C18 and maybe a phenyl-based phase, phenyl hexyl, or maybe even a biphenyl. And then a polar embedded phase is a good alternative, as well as a PFP phase. So, if you wanted to go with the alternative ones, you can even drop the C18 phase, because a lot of these are designed to be robust and stable. So, PFP, a polar embedded amide phase and a phenyl phase are the ones to go with. In our case for today, the phenyl hexyl halo, or the C18AR ACE column for the phenyl column, and then the C18 PFP or the halo PFP in the ACE and halo line respectively, and then the C18 amide for the ACE and the RP amide for the halo.
Our next question is, how does method development approach change when using a mass spec as a detector? Well,
Frankly, I don't have a lot of experience with developing mass spec methods per se. Certainly, with a mass spec method, you have to make sure that you have conditions and a column that can be used under the conditions that are going to give you, a good sensitivity for your analytes. And of course, you can use flow injection experiments for that type of an approach. But as far as some of these fairly complex methods, you see a lot of LCMS methods where not all the components are separated. And the key thing there is to, if you know what's present, to make sure that the ones that have the same mass are separated. And usually, you don't have too much crosstalk with the when you're using transitions from the acquired from the parent mass to a daughter mass. So usually there's not going to be too much interference in that regard. Of course, you have to also make sure that you don't have any of your either excipients or other matrix materials. You want to get your analytes away from the early part of the chromatogram so you don't have any interference from those as much as possible. Or if you have other ones that come out later in the run, you have to avoid those.
Our next question is, what's the optimal data acquisition rate on a DAD? That is, how many data points across a peak? And also, what is the optimal bandwidth? 214 plus or minus bandwidth?
Well, the data rate is what's best for your size column and the flow rate that you're using, and I certainly have a calculator that does that. But usually a rule of thumb is for assays, especially 20 to 30 data points across a peak or an internal standard. For impurities or even trace analysis, you definitely want to have at least 10 points across or 20 points across the peak. As far as bandwidth, that's another thing with a diode array that can be optimized, and it all depends upon what your wavelength of interest is, what the shape of your UV absorption plot is for one or more analytes, and so on. But I think from what I've read, at least with the Agilent literature, which is where I have most of my experience with using that instrumentation, is that the smallest bandwidth for the analytical wavelength is about 4. Usually they recommend somewhere in the 8 to 16, but there are approaches for figuring out how to optimize that. I may still have some of that information, or it may be available if you want to email me or info@macmod.com, mac-mod.com, I can pursue that further for you if you're interested. And for the bandwidth for the reference wavelength, you have to see whether or not the signal and the signal to noise is better with or without a reference wavelength. Usually it's better without it, but not always. And I usually use for a diode array a bandwidth of, anywhere from 50 to 100 nanometers. And if you're doing broad-based detection, you can actually use a broad bandwidth for your analytical signal so that you can make sure you don't miss anything. So you might have a 254 wavelength that you store, and then have a 50 or 100 nanometer bandwidth so that you can go all the way down to 204 and all the way up to 304, and you don't miss anything that absorbs in that region. Not for quantitative purposes, but for detection purposes.
Our next question is, which phases in the Halo and ACE product families do you think are the most useful to include in my method development?
I think the first question kind of dealt with that. A phenyl phase, a polar embedded phase, and either a PFP or a C18 phase are most useful. But sometimes like I said, that's why they call it column screening, because if we knew ahead of time, based on, even if we know the analytes, we can't necessarily know which column or which modifier in column or modifier column in pH is going to be the most useful. So sometimes it's a systematic, strategic approach to that, and you can't pre-digest it and figure out.
Our next question is, I see many column cleaning recommendations that use methylene chloride followed by hexane after an isopropanol flush. Does that really work?
I have never been very successful taking that approach. Most manufacturers recommend something like that, but if I feel like if I can't get the components off either by doing a water flush, sometimes there are things that require a water flush by itself. Usually I recommend organic plus water, but if that doesn't get it and 100% methanol or 100% acetonitrile don't get it, then 100% isopropanol. I don't use anything stronger than that because it seems like I've never been able to get a column to go back to its normal behavior after seeing methylene chloride and hexane. Maybe others have seen otherwise. It depends on what kind of samples the column has seen.
Our next question is, I thought that methanol was the preferred organic modifier with both phenyl and PFP phases. Should I even bother trying acetonitrile?
I think I mentioned that during the presentation, but yeah, you really can't tell. I mean, I have seen literature articles and reports that say that it makes sense that methanol should allow better access of the analytes to those types of phases, and even cyano phases, but in practice, through a number of different things that we've done in the laboratory, I haven't seen that necessarily always hold true. There's many times where acetonitrile works quite well and even better than methanol for certain of those phases like that. So I think you should try both if you're doing a holistic approach.
The next question is, why is the gradient delay volume important?
Well, I think the gradient delay volume is important to know because you want to document it so that anybody else in your own company, or if you're publishing it, or if you're transferring it to another location at your own company or another company, that they can repeat it. Once they know what their delay volume is on their instruments, then they can make the adjustments in the conditions so that they can closely or relatively closely replicate your separation. If you don't account for gradient delay volume and gradient delay time changes, then what you end up with is you can get movement and selectivity changes, relative movement of the peaks, especially those that have relatively early eluting times. So like in a 50 to 100% or 50 to 5 to 50% gradient, components that elute in the 5 to maybe 20% range are going to be potentially strongly affected by differences in delay volume. So for at least those two reasons, it's important to measure it and know it and document it.
Next question is, do you recommend to test PFP and C18 instead of C8 and C18 if you only have a chance to evaluate 2 columns for method development? The second part of that question is, are there any other advantages of PFP except for being more selective?
Well, the ACE C18 PFP was developed by Dr. Mel Ewerby, who worked at AstraZeneca, and he ran into some problems with some shorter chain PFP phases and phenyl phases, and that's what led him, when he was with iChrome, to develop longer chain C18AR and C18 PFP. That's not to say that, with the longer chain phases, certainly, if I had to choose one column, I would choose a long chain PFP column. I certainly don't recommend comparing a C8 and a C18 from the same manufacturer or even different manufacturers, because if it's different manufacturers, then you're getting into different degrees of silanol activity and things like that. So, I'd rather choose a C18 and a RP amide or a polar emitted phase from a given manufacturer than I would, say comparing a Halo C8 and C18, for example, or a ACE C18 and ACE C8, and that's because they're not going to be that different, more than likely. And a C8 is valuable in times where you're getting too much retention for analytes at the latter part of your run, but other than that, a C18 column is going to tend to be more stable and have less bleed, et cetera, than a C8 phase. So look at the diverse phases.
Next question is, you mentioned gradient steepness should be evaluated for method development. Is there a criteria? And then also, how should we determine whether it is acceptable?
Well, when I say gradient steepness should be evaluated, if you were working with computer simulation by running a gradient that differs from another gradient by a factor of 3, then you use those as inputs, and you can then see what the impact of gradient slope or steepness is on the resolution and separation. If you don't have access to computer simulation software, then if you're running a gradient, say from 5 to 95%, and you choose, I'm just going to pick a number out of the air, a 10-minute gradient, and you compare it versus a 30-minute gradient, and then also run one in between, a 20-minute gradient from 5 to 95, by looking at the resulting chromatograms from those 3 experiments, you can see, which one has more resolved components and what happens to the peak movement when you change gradient steepness. There really is no criterion for gradient steepness. It really depends on what happens to the peaks, how they move, and which slope gives you the best separation. That's assuming you're only doing one single linear segment gradient. Sometimes it's necessary to have a plateau in the middle of the gradient, although it makes it more difficult to transfer methods when you have multi-segmented gradients. But there is no criterion, and you just have to optimize. If you don't have the computer software for optimizing, you have to use variants of the initial and ending gradient compositions, as well as the gradient time to iteratively come to an acceptable solution. And you can always then try a little bit of iterations above and below those values and see what happens to your separation when you change them slightly, which is what you do in a method robustness type of a test.
The next question is, any suggestions on column and gradient selection for hexamethyldiamine analysis? Hexamethylene diamine.
I'd probably want to talk to somebody offline about that, but I mean, that doesn't have any chromophore. So I mean, if they're doing mass spec, I'd probably want to, have the person even email me directly at T and my last name at mac-mod, and we can exchange emails and discuss if you'd like me to look into it for you.
Well, unfortunately, we are out of time. I want to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, MacMod, for making today's educational webcast possible. You will receive an email alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Thanks to all for joining. We'll see you next time. Goodbye.